I think we can probably get started. It seems like we have a decent number of people. Some people might still hop in, but I think we can get started.
Okay, should I just go ahead then?
Mm-hmm.
Okay, thank you everyone for having me. I am Ezra Jampole. I work at Exponent Inc. in New York City, and I am virtually visiting Cornell as part of EERI's Friedman Family Visiting Professional Program. And I'm going to discuss legal and insurance disputes in earthquake engineering. I'll break this talk into a couple different pieces. One, I'm going to talk a little bit about EERI. Since there are so many students from the EERI chapter here, I hope to provide a little bit of encouragement for you to stay involved in EERI as undergrads, as grad students, as young professionals, and 50 years from now as seasoned professionals. So I'll tell you a little bit about my involvement in EERI and some of the programs, and then I'll talk about the main topic, which is legal and insurance disputes in earthquake engineering. I mainly do failure analysis as a job, and there are a lot of really interesting failures outside of earthquake engineering. So I'd love to come back and talk about some of those. But since this seminar is generously sponsored by EERI, I felt like it might be a little underboard if I didn't talk only about earthquake engineering. I also want to say that I like to make these sessions interactive, so I will probably pose some, well, definitely will pose some questions to the audience, and hope that people try to answer them. No pressure. It's okay to get it wrong, or if you don't know and you're just guessing, that's fine. I promise some of them will be 50%ers, so yes or no answers. And so those ones, you have a pretty good chance of getting it right. So I hope that encourages folks to speak up. Okay, I got the double slide advance already. So first, a little bit about EERI. EERI was established in 1948, and it is a leading nonprofit organization that brings professionals together in all sorts of disciplines that are related to earthquake engineering. Everyone has the goal in mind of reducing earthquake risk, though. EERI is primarily composed of engineers, a lot of structural and geotechnical engineers, but there are also geoscientists, social scientists, urban planners, involved as well. So if you're interested in multidisciplinary issues, EERI is one of the best organizations out there for that. EERI's flagship program is its Learning from Earthquakes program. EERI historically has sent multidisciplinary reconnaissance teams after large earthquakes, who then produce reports and findings, and that forms the basis for a lot of the research that is done in earthquake engineering. There's nothing like the lab experiment that you can run on millions of buildings at one time when there's an actual earthquake. So it's really important that we perform field reconnaissance. So I've been involved in EERI for about 10 years now. My undergrad institution did not have an EERI chapter, and I hadn't really heard of EERI other than tangentially when I was an undergrad. But I started to get involved when I was a graduate student and mentored the seismic design competition team at Stanford. And then I navigated a little away from working hands-on with the team to being a member of the Student Leadership Council, who planned the competition, and I was co-president of the council. And then as I was advancing in my graduate career, I started to get a little more involved in earthquake reconnaissance. And EERI always hosts clearinghouses on earthquakes where people upload their photos and their data and often articles and other information that is very useful for people who are looking for information about an earthquake. There's a lot out there in the news, and combing through that can take some time. So I started curating earthquake clearinghouses, and the first one that I did was a housing clearinghouse on the performance of housing following the 2015 Nepal earthquake. And I've done a couple since then, and now EERI has some more formal ways that people can get involved virtually with reconnaissance. I published an earthquake spectra, which if you're an EERI member, you have access to. It's one of the top technical journals in earthquake engineering, great papers from very good faculty members. That the involvement in the clearinghouses springboarded my involvement as a field team reconnaissance member. And so I've conducted field reconnaissance as part of EERI teams following earthquakes in Oklahoma, and Mexico. And I'll tell you a little bit about one of those so that you can get a sense of what happens on field reconnaissance trips. The earthquake I'm going to talk about is the 2017 Puebla Morelos earthquake in Mexico. So the earthquake struck at 1:14 p.m. on September 19th, 2017. There was normal faulting, and there was an earthquake early warning system, which you would expect would give people a little bit of notice so that they could get out of their buildings. Now, the early warning system is denoted by these triangles and squares, and it's along the coast. And the reason for that is that there's a subduction zone that causes very large earthquakes, like the very large 1985 earthquake that killed thousands of people in Mexico City. And so the sensors are there in that subduction zone. But in this case, the earthquake resulted in normal faulting in the middle of a plate over here. So the earthquake early warning system started going off while people had been feeling the shaking for 20 or 30 seconds already in some cases. So not particularly effective here. Also confounding was that the date, September 19th, that was the same date as the 1985 earthquake. So there were many drills going on in Mexico City, the earthquake. And the original earthquake was at 11 a.m. This one was at 1:14 p.m. And people thought that it was another drill. That's why the early warning system was going off. Certainly affects behavior. So one thing you'll notice on this map is, and I appreciate that it's in Spanish, but typically red is bad, yellow and green are better. So you have a more intense earthquake in the red zones. And we see this other red zone here that is separate from around where the epicenter is. And this is Mexico City. So Mexico City was not always a solid city. It was an island in the middle of a lake where the Aztec capital of Tenochtitlan was. And the Spanish gradually filled in most of this lake to control flooding. And so the consequence is that Mexico City looks like this today. And unfortunately, that filled in land has very soft soils. So when earthquakes come, there tends to be quite a lot of damage that targets buildings of particular periods in Mexico City. And this is something we saw in 1985, and this is something that we saw in 2017 as well. So I'll show you a couple examples of the structures that the reconnaissance team saw while we were there. This one is an auto repair building. And one thing you may notice is that the upper levels of the building seem to have a lot more walls than the lower levels. This first level just has these small columns. And so this is something that we call a soft story, where there's this vertical irregularity and stiffness. What tends to happen in an earthquake is the earthquake will come and it will concentrate the damage at the weakest level, which in this case is this first level. So sure enough, that first level collapsed. And I believe a couple people were killed in this structure. And if we look at the actual site, after the rubble was cleared, we can see a couple things that are concerning. There's unreinforced masonry, and there also are some columns that don't have any stirrups. And so that means that shear is not transferred very well through those, and they are quite weak. Here's another example of a structure in Mexico City. One thing that we often see when we have rows of buildings, and that's something that's very common in Mexico City and also certain cities in New York as well, is that the building at the end of the row will be most damaged in earthquakes. They act as a fuse for the rest of the row. And you can think about it like a building being confined by other structures on the side of it. So in this case, this building was not at the end of the row, but it extended taller than the building at the end of the row. So the first couple of levels were confined, but the ones above it were not. And sure enough, we saw a collapse at this particular level in this building. So to tell you a little bit more about the study that our EERI team did, is we focused on areas where there were seismic recording stations, because that enables us to know with some certainty what the intensity of the earthquake shaking is. And so we went to, I think, 13 recording stations, and we investigated all the buildings around that recording station. And so we have many data points of what the performance is of the buildings. So this includes both buildings that are damaged and buildings that are not damaged, as well as buildings that were damaged to various degrees. And so we recorded various attributes of the building. And we were able to use that to construct what are known as fragilities that relate the probability of some occurrence to an intensity of earthquake shaking. So here we see some fragilities of probabilities of different damage states, so minor, moderate, more severe damage, or collapse tied to a particular earthquake intensity. And we're using average spectral acceleration, which the seismic design team may be somewhat familiar with. And then we can divide that by buildings that were built before the 85 earthquake, after the 85 earthquake, of different heights, which is quite important because the earthquake, when it comes in contact with the soft soils, tends to target only certain periods of buildings with certain periods, and period is tied to height quite closely. So I hope that gives you a sense of the types of things that happen on EERI reconnaissance trips and the type of things that can come out of EERI reconnaissance trips. Lastly, some of my more recent involvement is I was co-chair of the Younger Members Committee of EERI until about a month ago, and thankfully I'm no longer co-chair. It's a bit of a time commitment. And lastly, something that I think folks on the call may be interested in is EERI has a travel study program where if you are not experienced in earthquake reconnaissance, you want to get experience, or if you're just interested in it, you can travel to different areas with a group and tour relatively recent earthquakes and look at how the area has recovered long term. So I was part of that program going to New Zealand in 2019. And here's a photo from that trip next to some fault scarp at the Leader Fault, which was a new fault from the 2016 Kaikoura earthquake in New Zealand. So I hope that has convinced everyone to become a lifelong EERI member. Some exciting EERI activities. There's really a lot of benefits to being an EERI member. There's the interdisciplinary aspect. There's the outstanding technical journals you have access to, webinars, seminars like this one, unless you're sick of me by the end, in which case maybe that's not a benefit. And I think EERI as an organization provides a very clear path to transition from being a student member to being a professional member through things like seismic design competition, the Student Leadership Council, younger members committees, and then the other committees tend to be very welcoming of younger members as well. So if folks are looking to get involved in professional organizations, the barriers for entry in EERI are much lower than I think they are in some other organizations. There are also some benefits for students, since I think everyone here is probably a student. There's this Friedman Family Visiting Professionals Program, which most years is in person. This year's unfortunately not. In addition to the seismic design competition, there are paper competitions and fellowships. You can get some of your schoolwork funded. And there are also travel grants to go to the annual meeting, which is a great place to network if you're looking for a job. And it's too bad that it couldn't be in person this year, but for anyone who's not a senior, hopefully you can benefit next year. I believe it's in Utah. And then of course the journal access as well. Earthquake Spectra really is a fantastic journal, and I hope people will check it out. So more immediately after graduation, I would encourage folks to join the Younger Members Committee, and this should say younger, not young, though I certainly like to be called young. That there are numerous active EERI professional chapters as well. And then EERI also has an internship program where they'll take interns who work in their headquarters in Oakland, California, and get to know all the players in the earthquake engineering community. And there are other ways to get involved too, but I think those are the ones I touched on the least up to this point. And one other benefit is if you're a student member, you get your first year of young professional membership for free, and then you get reduced rates for another 4 years. So there's some financial incentive to being a member as a student. Okay, so I think that's my last slide on EERI, and we can get to the more technical content of the talk. So as I mentioned at the beginning, I'm going to talk about legal and insurance disputes in earthquake engineering, which is what most of what I do now at Expo. So there are a number of different fundamental issues that arise, and I'll show examples of all these, but I'd like to talk about them in a more general sense first. There's performance issues, and that's when a behavior has not performed the way that it is intended to perform. So this is an example of that. This is another photo from Mexico City where a building collapsed. There are design issues. So if something has not been designed the way it was supposed to be designed, say after it's built, there are concerns that it wasn't designed properly and it couldn't take the earthquake loading that it's required to, or other things similar to that. There are construction issues as well, where something is not built correctly and needs to be corrected. So one example here that I have on the left is there was an allegation in an office building that the glass panels that separate the boss man from the proletariat who were working for him couldn't take the International Building Code prescribed lateral loads. There's a 5 pounds per square foot lateral load requirement. And that's because there was an allegation that they were not connected properly at the top of these panels. So I designed and built a mechanism to pull laterally on those panels in place in the functioning office building and see if they could take the load or not. And coolest part was that I modified a tripod game hoist that usually is used to string deer, which quite frankly is disgusting to me, but it turns out to be a very effective device for testing whether or not panels can take code prescribed loads. And construction issues, getting away from this kind of silly example that was all too real for a while, construction issues often crop up related to delay cases. So contracts almost always specify that if construction work is completed early, then there's some benefit to the contractor. If it's completed late, then there's some benefit to the owner. We will often investigate if there were delays on a project, what the causes of those delays, say it's the owner or the contractor or some supplier, and that has pretty large financial implications. And often at the root of these delays is engineering issues. If something was not designed properly or something wasn't built properly and had to be redone. So I stay away from the delay analysis. That's something for the contractors and more construction-oriented folks to do, but the underlying engineering reasons that can often lead to delays is something that I'll investigate. So how do we conduct these investigations? So there are a couple key questions that we try to answer. What caused a failure? Has the structure performed or been designed appropriately? If there's been damage, can it be repaired or not? And then who's responsible for it? And often the answer to that question may be split. There may be multiple parties involved. So what Exponent's typical involvement is that we're hired by attorneys, typically, for the owners, for designers, for contractors, for insurance companies, or any other stakeholder you can imagine to investigate and provide our independent expert opinion. Not what's in the interest of whatever party hired us, but our independent opinion on this is what happened, this is why we think it happened, this is who's responsible, answering some of the key questions above. So to conduct failure investigations, there are a lot of things that may go into it. Not all failure investigations have all of these, but we'll conduct visual inspections. So go on the site in person, take lots of photos. We'll perform destructive or in some cases non-destructive evaluations. We might hypothesize potential causes. Often if you show up and it's just a pile of rubble, you don't really know what happened. You have to think about different ways that it could have failed and then go back to design calculations and see, well, what was the most likely thing that happened. So we'll perform numerical modeling occasionally, although I have a personal rule that I try not to use software for things unless I really need it. And try to use first principles most of the time. We always will review contemporaneous information. It's important to put yourself in the mind of the designer a lot of the time. If new information comes to light after they had completed their design, well, they may not be responsible for taking that into account. It wasn't available to them. We will often write reports. If there is an opposing expert who has a differing opinion from us, we may rebut evidence given by them. And in certain cases, particularly in arbitrations, when something is in private, we will meet with other experts and we will try to hash out our differences before it comes to the next phase, which are depositions and then testimony as well in court. So all of these can happen in a case. Often all of them will happen, often only some of them will happen. So there are a couple examples that I want to show that touch on those three different types of investigations, the performance, the design, and the construction issues. And I'll jump right in with one related to post-earthquake insurance investigations in Oklahoma. And I think this is the part in the talk where it'll start to become a little bit more interactive, since I'm no longer trying to sell EERI to you or giving background. So first, to set the stage, what's happened in past earthquakes? So in the 1994 Northridge earthquake, there was quite a bit of damage to light frame structures in California. The estimate is that about 50% of the insured losses were to light frame structures, so mostly houses. And the total damage, the estimates vary, but somewhere between $25 billion and $40 billion are often cited numbers. So that means that we're talking potentially $20 billion in insured losses to light frame structures. The consequence of this is that insurance companies almost became insolvent. And that's not good for anyone, because if an insurance company becomes solvent, if you have damage that was caused by an earthquake, you might not get paid out for that. And that's a huge problem. So there's a critical role of experts in determining what damage was actually caused by disasters or other events. In this case, I focus on earthquakes. And what damage was maybe caused by other mechanisms or was pre-existing. So the case study that I'm going to show, there will be a little bit of a quiz for people on the call to discuss whether damage was caused by an earthquake or not. So the case study, I'm going to talk about the Cushing earthquake in Oklahoma. Was in November 2016, and I happened to be on the EERI reconnaissance team for this, but got involved otherwise afterwards. So one of the first things that I look at after an earthquake before going on site is the intensity of the event, so that I have an idea of what damage to expect. So here is the location of the earthquake. There's the epicenter, and then the MMI, the modified Mercalli intensity, is a commonly used measure for intensity of shaking, and we see that it's Roman numerals 5 and 6 around in this area near the epicenter. So USGS gives an estimate of what types of damage you expect to see. And by no means are these fixed, that if you see something that isn't this, it's not caused by the earthquake. This is an estimate. This is the type of damage that we see during these earthquakes. So in this particular earthquake, we might expect there to be some slight damage, and potentially if it ticked up a little above MMI of 6 into MMI of 7, there might be some negligible damage in well-designed buildings, but poorly designed buildings might be considerably damaged. So this is what I would expect going into the field after this earthquake. So I'll show an example of one structure that was not well-designed, that is not part of the insurance investigation, but gives you a sense that this earthquake could damage a structure. So this is a building in Cushing's historic downtown, and we can see that much of the brick facade has fallen off the structure into the street, and we can see that it's disconnecting from the building next to it. This is something I talked about earlier, that the building at the end of the row can be a fuse. And we also see, and it's hard to see in a photo, but it's easy to see in the field, that the building was leaning at least 1 degree, which is not good. So this is a building that is clearly compromised. It's unreinforced masonry. I would not advise going into this structure. And sure enough, it actually blew over, or the front facade blew over in a windstorm less than a year later, and it since has been torn down. So that should give you a sense that for a building like this, an unreinforced masonry building that's old, built turn of the century, the turn of the 19th century, sorry, turn of the 20th century, not turn of the 21st century, that there can be some real damage to structure. So for the insurance side of things, there were a number of schools that were allegedly damaged during the earthquake. Now, these school buildings are all typically located pretty close to the epicenter within that MMI 6-ish range. So here they're shown on a map. And to give you an overview of what these look like, this is some aerial photos of 9 of the school buildings. And the construction is mostly CMU wall with some masonry facade over it. There are other typologies in there. There's some steel framing. I think some of the masonry is reinforced, some of it is unreinforced. These are mostly 1-story buildings with select sections that are a little bit taller, like in a newer building and in gymnasium. So this is one example of a round gymnasium, which has its own interesting attributes to it. This is 2 stories. And then we'll look at one of these close up, and we can see, you notice the roofs are slightly different. So this one we might expect to be different. It's taller. This is a gymnasium or auditorium, but these are different because the construction is of different vintages. So built at different times. So that leads to some interesting performance during earthquakes. So now we get to the more interactive portion of it. So I walked into one of the buildings, And this is one that had not been occupied in several years from before the earthquake. And we see that many of the ceiling tiles are down in the building. We can also see that some of the grids that butt against CMU walls appear to be damaged. So does anyone want to venture a guess and give an explanation for why this may have been caused by the earthquake or maybe was not caused by the earthquake?
Could it have been that the CMU walls were transferring some of the lateral loads onto the ceiling grids, and so as a result of that, it was shaking loose like some of the ceiling tiles and generally like knocking that down?
So the CMU walls are probably not transferring load to the ceiling grid. So a lot of the load of the structure comes from the mass of the structure. And there is mass in the walls, but a lot of the mass is going to be in the floor diaphragms or the roof diaphragm. And so that will transfer load to the CMU walls, but most of that will be carried to the floor.
I guess you said the building was unoccupied for a couple of years before the earthquake, so maybe, especially with the ceiling tile, because I know they're not necessarily like structural components per se, maybe they're just like old and not really directly, like the damage is not really directly caused by the earthquake. But
so Anita hit on an interesting point, and that's the issue of non-structural components. So non-structural components are often the first thing to be damaged, as are contents in a building. So these are non-structural components, and they're very flexible, and ceiling grids tend to be damaged very easily during earthquakes, and they will shake back and forth and hit the walls, and that's why we see this deformation here. So it's not the wall hitting the grid, it's the grid hitting the wall. So in this case, this is probably caused by the earthquake. It really doesn't take a lot to get these moving. And sure enough, we see a lot of these grids fall out. And I think in almost all of the buildings, a significant number of grids fell out. Some of the dirt there might be because the building hasn't been used for a while though. So let's look at another example. And so this is in an occupied building. And something we saw is that a partition wall, masonry partition wall, shifted by an inch or so. And we can see where it's been dragged along the carpet here. Is this something that's caused by the earthquake?
if no one else is saying anything, I'll answer again. But I just want like everyone to get a chance to participate. But this, I think, I mean, it could be, but it could also be any kind of like roof load that's strong, right? But that usually happens in like the attic area. This is not the attic.
So I liked where you're heading with this, with the it could be. I think that's probably the right answer. So this is a partition wall. It's not bearing a lot of load other than its self weight here. So that means that if, say, the roof is deforming above it, it's not directly going to transfer to this wall. The wall is maybe mostly freestanding, and so it could, in theory, slide. But it's questionable whether this was caused by the earthquake. And maybe it was. I mean, we do see contents, and we do see partition walls shift during earthquakes. So I would tentatively say that this is something caused by the earthquake, but it wouldn't be unreasonable to say that it was not caused by the earthquake. So that would have been a good one for someone to answer, because no matter what you said, you can defend your answer and maybe be right. I probably should have done that first to encourage participation. So here's another example, and this is some damage to some concrete slabs. And this, interestingly, is at the interface between structures of different vintages. So I showed the photo earlier where the construction was built at different times. And here, this occurs at a location where the structures were built at different times as well. And so this is looking at the floor slabs. So is this something that is caused by the earthquake?
I would say maybe not caused by the earthquake, because like when you like build a new structure onto an old one, there's like, because you'd have to like somewhat, I guess, damage I would say like in the construction that you're like pouring new concrete onto old concrete, and like there might be some damage in doing that, but also like the interface between the old building and the new building would be sort of different, and like maybe that wasn't done too well, and it could have been caused by some other issue, like some other activity that could have happened in the building other than the earthquake.
Yeah, interfaces are tricky, and I think you're right that it was maybe caused by something else. So something that's common in Oklahoma is you see a lot of expansive soils. And so when you have buildings at different vintages, the soil is going to settle at different rates as well. In either case, you don't necessarily have a firm connection between those structures. So this might have initiated pre-earthquake, and then the earthquake may have caused these sections to move slightly differently. Maybe there were issues with the interface, but what initially caused this was probably not the earthquake. So this is a trickier one that maybe I'll talk through. So this is in a gymnasium in a building, and we can see these trusses that are supporting the roof, and they have this outrigger that supports another section of this roof. And then they come into the wall, this CMU wall, and we can actually see that this roof structure here, this ceiling, is not supported by the wall, it's supported by this outrigger. And so we see a separation between the wall and between the roof here. And that separation is probably not caused by the earthquake, since no load is transferred through here when you think about the load path of the structure. So it's much more likely that settlement is the cause of this condition. And something that we see on the exterior, and this is a similar location, not the exact location, but a similar location, we see some diagonal step cracks that are typical when there's differential settlement of the soil. So this separation and this opening that's coming up here is probably not caused by the earthquake. So another example that we saw in a lot of locations, and I've drawn a black line over it so that we can see it more easily, is cracks in corners. And this is something that we often see in earthquakes. If the blocks are not interconnected, if they're not interlocked, then we'll see this often. The consequence is that, well, you have a little bit of crack in the corner and you just need to apply some sealants, and it's probably good to go after that. Another area that we often look for damage after earthquakes is at openings. And so if you see cracks in the four corners of a window, then that's a sign that, well, the building racked one way and then it racked another way, and that'll cause those cracks to emanate. But when you only see them in one direction, not at every single corner, then that's something that maybe is not caused by the earthquake, it's potentially caused by something else, like differential soil movement. So here's another example that I'll pose to the audience. So in this case, some fascia board has come off of this awning, and we can see someone tucked it in to this handrail here. So is this something that was caused by the earthquake?
I feel like it probably could have just fallen off on its own.
That's a pretty good answer. This was one of the unoccupied schools, and I didn't even say that. So it could have come off on its own. Also, a likely culprit is wind. So this is relatively exposed to wind, and this is a type of damage that we often see during wind events. So unlikely this was caused by the earthquake. There's really no mass here that would move it and cause the fascia board to come off. So it's hard to imagine that could be caused by an earthquake. So here's another example. In this building, there were allegations that lots of cracks in walls were caused by the earthquake. And when we looked at the structure, we could see that there was a lot of joint material that had been put in. So someone had tried to repair this. Someone had already caulked this, and it was not a post-earthquake repair. So that's a sign that there were pre-existing issues at this site, potentially related to differential soil movement. So further cracks, it's questionable whether that would be caused by the earthquake. Another thing that we saw at these sites is foundations and that were exposed. And here we can see that, yeah, there's some cracks and maybe even a little spalling in this foundation, but it's very weathered. And so when you want to determine if damage is caused by a recent event or not, it's good to look at how recent it looks. If the cracks are sharp, if they appear to be weathered, if someone's painted over them, then that's a sign that it's probably not caused by the earthquake. So the last example I have is some horizontal cracks in the mortar joints of CMU walls. And so this is something that maybe was caused by the earthquake. However, we have to think about the consequences of this as well. And so we typically will go to various guidelines that are published by, say, FEMA, in this case, FEMA 306, that tells us that, well, this type of crack, yeah, may be caused by the earthquake, but you don't actually need to do anything to restore the structural performance of the building. So that's an interesting wrinkle in these cases. So in summary, you should consider the extent to damage and if the earthquake is likely to target particular elements. I think that wind one is a good example where it's unlikely that it's caused by the earthquake, but there's damage, maybe something else caused it. Identifying if there's weathering to damaged elements is very helpful in determining if it's caused by a recent event. And really think about, does it make sense that the earthquake would have caused this, or might there be other causes? And finally, it's important to consider the consequences as well. So if you looked at those cracks in the CMU joints and decided that the building was unsafe, then I would have a little beef with you, because that's not what the literature would support. So that's my first example. I'm now going to go to an interesting, maybe more exciting one. And this is a 12-story building on the West Coast. Now, this building was built in 1923. It has a reinforced concrete frame, and it uses hollow clay tile, or HCT, infill and partition walls. So what that means is that you have some blocks of hollow clay tile that fill up between the concrete frame and the floor. And so that provides some added stiffness to the structure. You think about it when the frame tries to deform, well, it's trying to deform all these blocks as well. So this structure was damaged during the 1994 Northridge earthquake and was subsequently repaired. So many years later, long after the Northridge earthquake, there were allegations that a water supply line leaked on the 8th story of this structure, and it damaged plaster on the wall. Then in the course of removing the plaster, the HCT infill was damaged. And the allegation is that that HCT infill is a critical portion of the building's lateral resisting system, and the earthquake resisting capacity was substantially reduced. So that's what the allegation is for the structure that I would investigate. So how are these allegations supported? Well, someone created a numerical model of the structure, and they used software by CSI, which I think the seismic design team is probably pretty familiar with if you use SAP 2000. And they modeled the structure, and then they modeled the infill as well. And a typical way of modeling infill is to use equivalent struts in your model. And so say a strut that can only take compression. So you put 2 in the opposite corners, and when the wall racks one way, it engages one. When it racks the other way, it engages the other strut. And so they model the infill wall in that way, using some literature to support exactly how stiff and how strong those struts would be. And so what they did was they modeled the structure in an undamaged state, and they modeled it in a damaged state. And in their undamaged state, they assumed that there was solid infill between every single column. So every column on the exterior, on the interior, we see solid infill. So we're looking at a plan view now. And then in their undamaged state, they said, well, this one wall was damaged, it got wet, the plaster was removed, the HCT was allegedly damaged. So we're going to take out all the infill on this wall, and we'll model the structure this way without this infill. And then we'll compare the results of these. So at first blush, does anyone have any comments on this strategy that someone used to assess how the structure would perform in an undamaged versus a damaged state?
I mean, I guess it also depends on, like, because the wall can be like a little bit damaged, but it can still hold some load. I don't know if this analysis considers that scenario, because it also depends on like which part of the wall is damaged. It might be more nuanced than just damaged versus undamaged, I guess.
Yeah, I think you brought up 2 good points. One, what's the extent of damage? Is it appropriate to take out an entire line of walls entirely? And 2, where is there damage? So I had shown you that the leak was here, but they've taken out this entire row. So anything else?
I'm not sure if like this is right, but also would those walls be like continuous, or there be doorways in between them to connect the different sections?
That is an excellent answer, and a very good point is you have to be able to enter the building somehow. In both of these configurations, there's solid walls everywhere. You are in a cell and you're trapped there for life if you're in this structure. So that is not a good way to model it. Perhaps it's an approximation, but it's certainly unrealistic. So I think that you guys hit on some of the major points. So another thing that they did was when they actually subjected this to earthquakes, and I'll be leaning on the seismic design team to answer some of the questions here. They took a very famous earthquake recording, one of the first ones ever recorded. This is the 1940 El Centro earthquake. And they scaled it down to 10% of what the original recorded earthquake intensity was in terms of peak ground acceleration. And they subjected their numerical model that we saw in the previous couple of slides to this very scaled down earthquake. And they used that to support their conclusions regarding what the consequence was of the damage. So are there any issues with doing this?
I think one of the ones that I see immediately is they alleged this was damaged in the 1994 Northridge earthquake, which...
So I'll jump in. It was damaged in the Northridge earthquake. That's just a fact. It was repaired. And then this is another event that happened after that. So that's just background information. So I didn't mean to confuse with that piece. Okay.
I think where I was going with this is more, I don't know if the ground motion that they used, like the 1940 El Centro earthquake, is accurate to, like, the intensities and frequencies are accurate to the ground motion the building actually experienced.
Exactly. So this is not representative of the shaking it experienced. If it already went through the Northridge earthquake, then we have many recordings from the Northridge earthquake. Why not, in your analysis, subject it to something that the building could actually see? So that's a very good point. And another point is related to, this is very tiny. 0.03 Gs is really small. And so we'll come back to the importance of that. So first, we tackled the conceptual point of, does the HCT actually resist earthquake loads in the first place? So conceptually, the answer is yes. So if you have filled in a frame, so this, we're looking at some columns, and then we see some beams or some slabs, and you have it filled in solid, then you probably are providing some stiffness. You get some strut action here. And codes and standards will agree with you, and there are ways to model that. The problem is that, as someone pointed out, that when you start adding openings, you significantly reduce the strength and the stiffness. So we'll focus on stiffness here, but if we put just one window opening in, that's 12.5% of the area in this frame, you get a 30% reduction in the stiffness provided by the HCT. So one small opening significantly reduces the stiffness. If you have a couple doors, and this was a typical situation that we saw in this structure, people like to have doors in their buildings, you've reduced 42% of the area, but you've reduced 84% of the stiffness of the structure. So you're really not getting a whole lot out of that HCT if you had a lot of openings. So if we consider that some of these are partitions, the HCT isn't coming up all the way to the underside of the beam. At the exterior, you have windows everywhere, you have doors at lots of them. Some of the partitions don't line up even with the column lines, then you probably aren't getting full HCT at every single column line. So this is what the actual layout of the building looked like. And sure enough, we see those windows all around the exterior, these partitions that have many openings in them. So the consequence of this is that the way that structure had been modeled, there was a significant overestimation of the contribution of the HCT infill to the initial stiffness of the structure. And also results in an overestimation of the potential torsional irregularity in the structure. So our investigation looked at what the actual intensity of shaking was in an earthquake that this building had actually had felt. And so there was a seismometer in the Northridge earthquake that was less than a mile from the building. And so if we compare the intensity of that earthquake from the Northridge earthquake to 10% of the El Centro earthquake, is more than 10 times as intense. So I'll pose the next question to you. What are the consequences of someone analyzing this building at a very low intensity instead of analyzing it at a higher intensity? Well, we've identified that it's not realistic, but what's the real consequence of that?
I guess some materials, like they perform elastically to a certain extent, but once you like scale up the earthquake, it loses its, property, like elastic property, so it kind of breaks. I feel like the scaled down version might be insightful in that you can get some maybe modal information regarding the building when everything's elastic, but that's not always the case when you have a severe earthquake.
Yeah, you're absolutely right about that. Is once you start to get inelastic behavior of the materials, then the performance changes quite a bit. And in particular, something like an infill material, where you expect that once you go nonlinear, really you start to see blocks that come flying off. And so then you lose your stiffness all of a sudden. And so I'll try to conceptually explain this as if something is completely linear, as the earthquake intensity increases, the displacement goes up and there's a linear relationship there. Now, if we look at how the force and the displacement are related for the concrete frame versus for the HCT, where our concrete frame is initially stiff and then it flattens out, and then it starts to lose stiffness as you continue to increase the displacement. Very common behavior in all types of structures. Which the ACT, at low deformations, the way this was modeled was that it would have high stiffness initially when that infill was really compacted. And then as HCT increases in deformation, it has reduced stiffness. So let's say that you expected an earthquake that would have high deformation. The stiffness would be very low from the HCT. It wouldn't contribute very much to the earthquake response of the structure. But at low deformations, it has pretty high stiffness, so it contributes more. So by analyzing the structure at a lower intensity, you're overemphasizing what the HCT contribution is to the stiffness of the building. And so you would consider that it would be much more important to the lateral resisting capabilities of the building than if you used a more realistic estimate of the earthquake intensity. So we analyzed this structure using the models produced by someone else, and then adjusting the models and subjecting it to the Northridge earthquake that the building had actually experienced. And the amount of displacement at the roof of the structure with 10% of El Centro was very small and really was not so different between the damaged and the undamaged response ultimately. And in either case are far less than the displacement the building had already undergone during the Northridge earthquake and had already been repaired for. So we found one, and this was more of a material science thing that one of my colleagues looked into, but there was no evidence of damage to the HCT. So that almost takes out the argument on its own, but also that the HCT had a limited effect on the lateral capacity of the building. And the building had already undergone much larger earthquake than that contrived 10% of El Centro. So I would say in summary that the analysis that was performed by others could have been a little bit better, could have been a little more realistic. And when you correct for those things, really the impact is quite limited from the alleged damage to the structure. So I'll show one last issue that doesn't have to do with performance or to alleged damage, but has to do with design issues. And so this is an underground metro system in a high seismic region. And here's a photo of, not of the underground metro system, but of another one so that we can be in the right mindset. So a little bit of background on this project is that the municipality was adding a new underground metro line in a high seismic area. And the contractor filed for compensation for delays that they say were caused by the owner raising concerns over the earthquake-resistant design of the metro stations. So I talked about earlier how there were often disputes when a project was delayed over whose fault it was. And in this case, the contractor has said the delay was caused by the owner. The owner raised concerns with the earthquake-resistant design. They shouldn't have. That's the reason why we were delayed. So pay us some money, and it was hundreds of millions of dollars that they were asking for. So I'm going to tell you a little bit about the initial seismic design, and I think this will be a trickier one for participation, but I hope people venture a guess. And then I'll point out some of the issues, and we can talk about whether the owner was right to voice concerns. So the original design used what's called importance factors, and so that's something that's used to adjust what the elastic forces that are applied to a structure to. You adjust them based on how important the structure is. So importance factor of 1, that's a regular structure, and then something that's less important. Often unoccupied buildings, you might use something lower, and a more important structure, you might use something higher than that. And there's different interpretations of the meaning of importance factor, but conceptually, you're designing for higher forces, or you're designing to have better performance during the same return period event. A couple ways to look at it. But in this case, there was an importance factor used for what's called important structures. There was a linear elastic analysis of a single station under a 1,000-year return period earthquake. And based on those, the contractor concluded that the structure would behave essentially elastically under this earthquake, and that the design was suitable. So the question to us was the owner right to voice concerns for a design that has this importance factor for an important structure, was designed using linear elastic analysis of a single station under a 1,000-year return period earthquake? And there were a couple other issues that I won't get into that are more geotechnical focused. So any thoughts on this? Any problems with the design? So let me pose this a different way, because I think it's mostly undergraduates who are attending, and I don't mean to offend anyone, but this is more the type of material you might start to cover in graduate courses or as a working professional. So what would you do to investigate whether or not the owner had the right to voice concerns here? Let me phrase it that way.
I would probably first check to see, kind of evaluate like the seismicity of the region that the structure is being built in, to understand if like on a 1,000-year return period is enough, is like a big enough time period to analyze. Because I know in areas of like high seismicity, you want to prepare for events that come at larger return periods, just to be on the safer side.
Yeah, so background research on seismicity, that's good. Anything else folks would do to investigate this?
I guess kind of going off of what we talked about a couple of slides ago, maybe we also need to investigate like the nonlinear behavior of the structure a little bit, just because I think because it's mostly concrete, right? So reinforced concrete, maybe there's some nonlinear behavior that's ignored. But I guess the importance factor, that's a pretty decent factor for a structure, right? Because I think most structures just factored as 1. So like, if I were the owner, I wouldn't be super concerned, but like, I don't really know the whole story. So.
Yeah, so that importance factor and what you should use is an interesting topic. So what I would do to investigate this is what types of importance factors are used for similar structures? What do the design codes say you should be using? What do the design codes say your return period is? You touched on some interesting things related to nonlinear analysis that I'm definitely going to come back to here. So first, we'll start with importance factor. So 1,000-year return period, that's something that is often used in bridge design. And in the US, in building design, for example, we'll design structures based on forces during what we call a design earthquake that is typically a 500-year-ish return period. It's actually 475. And then we'll make sure that they have a suitable probability, a low probability of collapse during a 2,500-year earthquake. So that's how we typically design things, and those can get shifted around a little bit depending upon the project, but that's quite typical. So in this case, we did research into what importance factors are for similar structures, the other metro stations, and found that it's actually more acceptable to use an importance factor of 1.5 instead of 1.3. And so a simplistic way of looking at this is, well, if you increase your uplift on earthquake forces from 1.3 to 1.5, how does that affect the return period of the earthquake? And the effect of this was going from an earthquake with a 1,000-year return period to one with a 2,500-year return period. That's one way to think about what the effect is of changing that importance factor. And so this could be very site specific, but it is a larger event that should have been accounted for. So another point that was touched on was the need to perform nonlinear analysis. And so I'll conceptually show this. In a linear analysis, the force and displacement are proportional always. It's linear. In nonlinear analysis, as you increase displacement, you reach a point that you no longer have to apply additional force to increase the displacement, and eventually you lose strength and you get a collapse. So the consequence of including nonlinear behavior versus not including nonlinear behavior for earthquakes of the same intensity can look something like this, where we conduct a response history analysis, and the displacement with linear analysis looks something like this, relatively small deformations. But when we include the nonlinear behavior of the system, we see this ratcheting type behavior, and we see a large permanent deformation of the system. So another thing that was done that was incorrect is that there was an analysis of only a single station. And so this is a typical seismic map of a metro area. And when you have multiple stations, you will have very different intensities potentially at the different stations. So it's important to perform an analysis of each one. You may have different soil types at each station too. So even if you expect the same rough intensity of earthquake, the way that an underground metro station will interact with that structure could be quite different. So after the concerns were voiced, subsequent seismic analysis was performed by the contractor, and they conducted a nonlinear analysis of a single station still using the 2,500-year return period earthquake. And they used a single earthquake ground motion to represent the hazard at this site. And so there are a couple issues with this as well. Using a single ground motion is not appropriate for representing hazard at a site. What current codes and standards say, and I'll use ASCE 716 as an example, it's minimum loads on buildings. You need to use at least 11 ground motions if you really want to understand things like collapse and performance during more rare earthquakes. So using a single ground motion is not a good representation of the site. Another way to illustrate this is, let's take an earthquake that has the same intensity by one metric, and we'll subject the structure to it. So in this case, we'll use peak ground acceleration as the measure of earthquake intensity. And these two earthquake recordings, they have the same peak ground acceleration, this one in orange and this one in blue. But we see different response in the structure because, as you can tell, just because this one peak point is the same, this peak acceleration, actually I think it's up here, this peak acceleration and this peak acceleration, doesn't mean that the rest of the record's the same. You have very different frequency content, you can see a very different response. And sure enough, we see that one of these earthquakes that has the same peak ground acceleration has maybe 30, 40% additional deformation that it causes in the structure. And so that's significant. So in summary, we found that because of these issues related to the importance factor, analyzing the structure using linear analysis instead of nonlinear analysis, and then some of the subsequent analysis that only looked at a single ground motion, it was appropriate for the owner to raise concerns with the seismic design and analysis of this metro system. So that's it for my examples. I hope those were informative, and I have a couple parting words that I hope are helpful. So you probably want to avoid a failure analysis if you're a designer. So I recommend read the codes and standards when they come out, stay up to date on the latest research. And an important thing is don't decide out of your depth. A career is a marathon, not a sprint. You don't need to know how to do everything right away. You should start from your core expertise and then expand your knowledge slowly from there, and you won't get into trouble. On key decisions, think about how you would testify regarding those decisions, because you might end up testifying as a fact witness one day about a decision that you made as a designer. And one way to surely stay out of a failure analysis in structural engineering is to drop out of structural engineering, though I hope that no one does that who's on the call today. So how do you get involved in a failure analysis? Well, you can ignore the things on the previous slide, but all kidding aside, I recommend staying in school, doing a master's or a PhD. You get a lot of additional coursework that's very useful for analyzing particularly complex structures and just understanding the way that different types of structures behave during earthquakes or other events as well, like wind, hazards, deterioration. And a PhD is helpful because you learn to really dig into the weeds, though it's not strictly necessary for getting involved in failure analysis. So with that, thank you for hosting me. Thank you to the Friedman family for sponsoring this seminar and connecting me to Cornell. I'm happy to answer any questions now. And if folks want to connect with me afterwards, I'll leave this slide up. Feel free to email me. I have my email address here. So thank you.
Thank you, Ezra. I guess I have a question, because we were kind of talking about towards the end the importance factor and ASCE 716, which I know is kind of like the current, most updated standard for determining like loads and stuff. I guess I know nowadays a lot of people talk about like performance-based design and things based on, I guess, a more detailed analysis, sometimes even involving like finite element. What do you see, I guess, as the advantage of doing that or disadvantage of doing that versus just basing it off of building code? And what do you think? Do you think the building code has room for improvement?
Well, the building code certainly has room for improvement. There are a lot of advantages to performance-based design. You can target and translate performance into something that people actually understand. So we tend to think of performance-based design boils down to three fundamental issues: deaths, dollars, and downtime, and representation of what the likelihood is of any of those three potential outcomes. And those are things that owners understand. They might not really know their tolerance for them, but if I tell an owner that it's likely to cost them on average $20,000 a year for seismic performance, it doesn't all happen in 1 year, it happens when you get an earthquake eventually. That's something that they understand much better than telling them that they're gonna have story drift ratios of 0.7%. That doesn't mean anything to most people. Owners, it doesn't mean anything to a lot of engineers as well. So there's a lot of benefits to performance-based design from that perspective. It's understanding and being able to target the performance during different frequencies of earthquake. I think performance-based design can lead to better designs as well if you let it. It can also lead to cheaper designs as people figure out that, well, I don't necessarily meet the prescriptive standards in the code, but I can justify doing this with performance-based design that meets the code intent. It's not necessarily a safer building, but it's probably a cheaper building.
I had a question on like the actual like situations that you like provided to us. Like were those like those happen in real life, I guess? Like
Yes.
the one about like the subway station. And did they have to perform more like was it time histories on the analyses? Or they only use like one ground motion, and like did that like pass, or what did they do about that?
I think they ultimately did change the way that they were analyzing the structure, but the part of the dispute that we were involved with was actually separate, as whether or not it was appropriate for the owner to raise those concerns. And once the owner tells you to do something, then it's hard to say no, whether you agree with it or disagree with it. But you can say, well, you should pay us all this money for it, if you think they shouldn't have said anything.
So like the dispute would only happen if someone like says the owner shouldn't have asked them or something like that, or like.
Yeah, so if in this case there was quite a bit of money at stake because of the way the contract was written, there was a delay to the project because of the reanalysis that was done at the request of the owner. And so the dispute, and this is fairly common, is if the owner shouldn't have said anything because the design was fine, versus if the owner was within their right to say something because there were legitimate concerns that should have been picked up by the contractor, by the designers. Then that's what the dispute is really over, whether or not they can raise those concerns or not, because raising them is what led to the delay. So it's basically figuring out whose fault is the delay on the project. And in this case, the underlying reason is related to this engineering issue.
Yep.
I guess I have another question if nobody else has. So sometimes, you know, like I think one of the earlier examples, we kind of see situations where the building had some settlement or certain damage that already happened, and maybe the earthquake kind of exacerbated, you know, like the damage. In that case, how would you divide the responsibility? How do you come up with a percentage of how many percent, like 70% of responsibility belongs to this person versus, you know?
Yeah, so we typically won't come up with percentage of responsibilities, but what we would do is we might say conceptually, this is what needs to be repaired to repair the condition that was caused by the earthquake. And then someone with a construction background will then price how much it costs to perform those repairs, to repair the earthquake damage, to restore the building to the condition it was in prior to the earthquake, which might not have been a great condition.
Right. Okay. Interesting.
I had a question sort of about kind of some different analysis cases you've done. Is it mostly like modeling-based analysis where you use software to kind of model the structure and model it under different ground motions in different scenarios to see how it would perform? Or is it generally more field-based where you go and actually see damages to the structure and report based on those?
So I try to avoid using software as much as possible, not because I'm not good at it or because I dislike using software. It's that a lot of times it's not really necessary because you can figure out what's happened without doing an analysis. You can look at what the conditions are in the field and you can develop the hypotheses and which ones are most likely. And then you might use analysis to confirm. Now, there are cases where something is really complicated and you really have no idea, and then you probably need to turn to modeling, or cases where the issue is with the design. So, for example, if someone alleges that the structure can't resist the intensity of earthquake, that it has to, with sufficient probability of not collapsing during a certain intensity of event, then yeah, I'm going to need to create a computer model and subject it to a probabilistic representation of the earthquake, a whole bunch of different ground motions to figure out if I agree or disagree with that allegation. But a lot of the time, we can avoid the computer and spend a lot of time taking photos, thinking about first principles and what common failure mechanisms are. If there are any other conditions, like say corrosion that deteriorates a structure, it might lead to some failure.
And I guess going off of that, in the field, I think you mentioned non-destructive testing. What is that process like? I know a lot of people now use like sensors or even for concrete like impact echo or stuff like that. But what are some techniques, I guess, you can use to assess damage in the field without, you know, damage in the building?
Yeah, those are two good ones. Equipment that tells you where the rebar is located, I think is an important one. Just taking measurements, honestly, is probably the most important thing. You learn a lot by doing the destructive testing as well if you need to on, say, concrete strength, that type of thing. But quite frankly, I don't do a lot of non-destructive testing. It's relatively rare that I've had to do it. Any last questions on the presentation, on EERI, or anything else? Transitioning from school to working?
Oh, that counts. Okay. I don't know if it's relevant to many people here because I'm a senior. I'm one of the few seniors here at my BD. Oh, actually, there's one other senior here, but I'm going to get my PhD starting next year at Princeton University. So I'll be straying pretty far away from earthquake engineering. Not gonna lie, it's more on the building material side, studying concrete. More specifically sustainable cementitious materials. But I guess I'm just wondering what pushed you to, do a PhD and then go back to industry to do the job you have now.
Yeah, so I always thought that I was going to go into academia. So I, towards the end of my PhD, got more interested in consulting positions and the idea of working on many projects at one time, things that don't last always for 10 years, like academic research projects, but have a little bit of a shorter time frame. So that was appealing to me. So that was why I came back. Why I did a PhD in the first place? I went to Northeastern for undergrad, and there was a co-op program, and so I effectively worked as a design engineer for 2 years by the time I had graduated, and that was nice. It was interesting, but I wanted to get a little more into the details of the way buildings are designed, the way buildings perform, and going to graduate school was a great way to learn to do that. Both the master's, and then I started doing research as a master's student and continued on doing more of that as a PhD as well. And I just was fascinated with the way structures perform during extreme events. It didn't hurt that when I was a senior in college, near the end of my senior year, there was a very large earthquake that some of you may remember, the Tohoku earthquake in Japan in 2011. And that certainly was motivation to do research into earthquake engineering.
Cool. Yeah, I can relate. I mean, I've never had a co-op, but with internships and stuff, yeah, I do feel like sometimes I want to do more and just getting to like the nitty-gritty of things instead of just, designing. So I can relate. Yeah, thank you.
Sure.
Does anyone else have any questions? Okay, it seems pretty quiet now. But yeah, we're really thankful that you can, virtually give us this lecture. It's been a really good experience, and I think we all learned a lot. It's very interesting. It's the part of, I think, structural engineering that you don't really hear that much about, but it's definitely a field that's doing a lot of really interesting work. So thank you so much.
Yeah, no problem. I was happy to come here. Glad to talk with all of you. And again, if anyone wants to follow up with me, feel free to email me. I'm happy to chat with anyone further by email or phone, or I guess we all do video calls now. But yeah, it was, thank you very much for having me.
Yeah.